Okay, these are the section 2.3 part 1 video notes, and we are going to continue kind of looking at properties of functions. So we're going to kind of continue just talking about functions and all their general varieties, kind of some of the things that describe them, working towards looking for proper mathematical words to describe their graphs, etc. So we're going to start off talking about even and odd functions. Now, I know that you guys are used to working kind of with even and odd functions when it comes to polynomials. And when you talk about even and odd functions, you were probably just referring to their degree. Now, we have to consider that if I say a function is an even degree or an odd degree, that's not the same thing as saying the entire function is even or saying the entire function is odd. To say that a function is even or odd has a very, very specific meaning. Even and odd degree applies to the exponent of highest power in the polynomial, and we're going to go into greater detail on that in chapter 4. However, right now, when we're talking about an even or odd function, we've got a very specific definition. And what that is a function is even if the domain of if the number negative x and the domain f of negative x is equal to f of x. So if f of negative x is the exact same thing as f of x, well, then we're looking at an even function. And even functions have y-axis symmetry. So that means if you fold it over at the y-axis, you would create basically something that lies on top of each other. A function is odd if for every number of x in its domain, the number negative x is also in the domain f of negative x, but it's equal to negative f of x. So if you plug in f of negative x and then it's the equivalent of f of negative x, well, then you're talking about an odd function. And an odd function has symmetry about the origin. So if you were to fold it in half diagonally at the origin, again, that function would lie on top of itself. Now, I realize all these words are slightly confusing. It's a very mathematical definition. What does this mean? How do we apply it? Well, there's two ways we can figure out if a function's odd or even. The first way is we can look at the graph. This graph A is going to be an even function. Now, how do I know that it's an even function? Well, it's got y-axis symmetry. I want you to imagine that you're grabbing this graph on both sides of the y-axis and then you're folding it like a hot dog. It's very clear to see that, okay, if I fold this in half, this side is just going to end up on top of that side. So that means it's even. As I fold it across the y-axis, I've got the symmetry. And I'm actually going to jump to C because I think explaining B needs a little bit of an explanation from C here. C is odd. And C is odd because it has origin symmetry. Now, seeing origin symmetry is a little bit more difficult than seeing y-axis symmetry because it's really easy for us to picture what it looks like when you fold something in half. It looks a little bit different when you're folding this diagonally. So what I'm essentially saying is that I'm taking this entire thing and I'm rotating it this way. I'm going to fold it on top of itself. Or I could also think about rotating it this way to fold it on top of itself. When I do that, when I kind of do this diagonal fold, and again, when I do this diagonal fold, maybe this will make it more clear. I'm going to fold it across this line, y is equal to x. So I fold it over this line, and when I do so, these functions will lie on top of each other. So that means that I'm looking at a function that's odd because it has this origin symmetry. Now finally, B. B doesn't have y-axis symmetry. We can see if I fold it across the y-axis, it's not going to lie on top of each other. And then it's even easier to see that if I have this line y equals x, well, I definitely don't have any origin symmetry here. It can't even come close to lying on top of itself if I fold it across that line. So it's got neither y-axis or origin symmetry, so this means that it is neither even nor odd. So it's just neither. All right, now doing it on the graph is not like the easiest way to do it because you would have to graph it. When you look at a graph, it's easier. And if you already have a graph function, it's easier, but that's really not what I'm super concerned with. If you're given the equation, prove it algebraically. Proving it algebraically is a lot more than just doing a basic level eyesight test of a graph and saying, oh, well, this looks kind of symmetrical to me in this way, in this shape, way, or form. So I'm just going to either identify it as even or odd. If you can do it algebraically, that's going to give you the actual response. So what we have to do to figure out if a function is even or odd is your first step is to always figure out what is f of negative x. So what you do is you plug negative x into your x value. So for this first one, I get negative x squared minus 5. Well, any negative number squared is just itself as a positive number, so this is the exact same thing as saying positive x squared minus 5. So f of negative x is equal to x squared minus 5. Now notice, x squared minus 5 and x squared minus 5 are the exact same function here. We can all agree that x squared minus 5 is equal to x squared minus 5, which means that f of x is equal to f of negative x. And if we go back up to this slide up here, we see that a function is even if f of negative x is equal to f of x. And I've written that same thing down here. So that means I'm looking at an even function. Once we know a function's even, we know it's not odd. I don't have to do any tests for odd functions. I just know that I'm looking at an even function. If I go to example B, I'm looking at g of x is equal to x cubed minus 1. I'm going to go ahead and plug in g of negative x I get g of negative x is equal to negative x cubed minus 1. So when you cube a function, if you're cubing a negative number cubed is still negative because it's a negative times a negative, which makes a positive, times another negative, which will complete becoming a negative. So I can look at this, I can say to myself, x cubed minus 1 is not the same as negative x cubed minus 1. So right away, I can say that this is not even. Well, if it's not even, then I'm going to go into my test for odds. But what should my test for odds be? Let's go back up and look at this function. To figure out if you have an odd function, f of negative x has to be equal to negative f of x. I don't have negative f of x yet. All I have is f of negative x and f of x. I need to figure out what is negative f of x. Well, negative f of x just means you multiply f of x by negative 1. So I take negative 1 and I multiply it out to x cubed minus 1. This gives me negative x cubed plus 1. So this is negative f of x is equal to negative x cubed minus 1. Well, again, now I've got negative f of x, and I see that negative f of x, and all of these should have been g of x, I apologize. I see that negative g of x is not the same as g of negative x. These two are not equal. And since they're not equal, it's also not odd. So my answer here is just neither. All right, so again, I've got a U-try here, so this is kind of a throwback to when I was doing notes in person. My advice is for you to pause the video right now, look at these functions, just try them on your own. See if you can do them, and once you get your answer, or if you're struggling in the middle, start the video back up, see if my answer matches yours, or get to the point where you're struggling with, see what you did wrong, see what the next step is, and then go from there. But I do advise that you take just a second, pause the video, and give these a brief attempt. Okay, so again, I'm determining if these are even or odd. And the first test I always do is an even test. I'm going to plug in h of negative x, so 5 times negative x cubed minus negative x. H of negative x is equal to negative 5x cubed, because again, if I cube a negative number, it stays negative. And then I'm going to add x because I have that minus a negative. And for all of you that I taught in Algebra 1, that means you dip the chip and you turn that into a positive value. Right away, I can see, all right, these two are not equivalent. 5x cubed minus x is not the same thing as negative 5x cubed plus x. All right, so it's not even, which means that I've got to do my next test of, is it odd? And to figure out if it's odd, I got to find negative h of x. So I say negative h of x is negative 1 distributed to this entire function. 5x cubed minus x. When I distribute that -1, I get negative 5x cubed plus x. And that's negative h of x. Well, right now, negative 5x cubed plus 1, or plus x, is the exact same thing as negative 5x cubed plus x. So that means I've got h of negative x being equivalent to negative h of x, which means that I've got an odd function. Perfect. All right, and then for b, this one's probably the easiest one I gave you. We're going to do our test for even. I'm going to do f of negative x. I'm going to set that equal to the absolute value of negative x. And again, the absolute value is just talking about the distance from 0. It's not talking about the distance from 0 with the direction. It's a purely magnitudinal value with no directional whatsoever, aka a scalar. So I get f of negative x is equal to the absolute value of x. And therefore, we can say that f of negative x is equal to f of positive x, which is even. Also, you could have thought about the graph of the absolute value of x. I know that you guys covered these a lot in Algebra 2. So we've got that, and we all know that the base level graph for the absolute value of x is just that V shape. I am not a good artist whatsoever, so if I drew this well, you would be able to see the y-axis symmetry to make this an even function, but I drew this very lopsided, so it doesn't look like it has y-axis symmetry, but trust me, if you were to graph this on Desmos, it would. All right, now, again, we kind of get back into reading a graph, and historically, this is something students have struggled with, especially when we start reporting things in terms of x values. But being able to describe when a graph is increasing, decreasing, and finding its maximum and minimum are absolutely essential, and we need to know what these terms mean. Next year, when you get to AP Calculus, I guarantee you there's going to be a question on the AP Calculus exam that tells you the first derivative is either positive or negative, and determine whether or not that means the original function is either increasing or decreasing. And you'll learn that when the first derivative is positive, it means you're looking at an increasing function because your rate of change is increasing. And when your first derivative is negative, or when you're looking at a negative value of your first derivative, you're looking at a function that's decreasing because you have a negative rate of change. And I understand that all of that right now might sound absolutely crazy to you and you have no clue what I'm talking about. You don't know what a derivative is. But by the end of this lesson, you'll know what increasing and decreasing are. And I really, really want to emphasize how important this is. You're going to spend weeks in calculus talking about functions increasing and decreasing. It is such a large part of that course. So you need to understand this by the time you leave this year. It might take some of you a little bit of time, but you'll get there, I promise. So a function f is increasing on an open interval I if for any choice of x1 and x2 ni with x1 less than x2, we have f of x1 less than f of x2. Really mathy definition, but what does this mean? This means as I move from left to right, I'm going up. So again, just like we read books in math, we read left to right. I read this graph left to right now, and all I'm saying is I've got 1 point on my left side, I got 1 point on my right side. And as I move between that point on my left to my point on my right, I'm going up. This final point here is at a higher orientation than this point here. I realize that I'm kind of drawing them off to the side. I'm just showing you where their levels are. And we can see that at no point does it change this direction. It's constantly going up and up and up. So what I would say is that the function is increasing from x1 to x2. And we're always going to report this in terms of our x values. We don't report this in terms of our y values. That's something that a lot of students tend to get stuck on, is we think that we're reporting this in terms of the entire ordered pair, or we're reporting this in terms of the y value. We're not. We always talk about our graphs when we're talking via x terms. Always we talk about x terms. X terms are the independent variable. You cannot manipulate your x. The y gets manipulated because of the function that x is being put into. So we always, always, always report in terms of x. It gives us a hard, very firm, defined value that we can work with. Now, a function decreasing. Again, we've got this very mathy definition. A function f is decreasing on an open interval I if for any choice of x1 and x2 in I, with x1 less than x2, we have f of x1 greater than f of x2. So again, we're still talking about reading left to right. That's what we're saying. x1 has to be less than x2. And we can see here that they're defining x1 here and x2 here. What this means is that we've got a point that starts high and then ends low. So as we go from left to right, we're going down. A really easy way to think about this is go all the way back to Algebra 1. If you had a positive slope, you were increasing, and you could see that because as you counted your steps, you would say up blank over blank, up blank over blank. And if you had a negative slope, you were going down left to right, and you could remember that because you would say down blank over blank, down blank over blank. The exact same concept is applying here, where we're thinking about if it's going downwards as we move to the right, it's decreasing. If it's going upwards as we move to the right, it's increasing. That's all we're trying to say here. A constant, a function f is constant on an open interval I if for all choices of x and I, the values of f of x are equal. So if you ever have a straight line, you say your function is constant. And that's this is about as straightforward as it can be, and this is a scenario where you would have f of x is equal to c. Again, in algebra, you were really used to seeing y is equal to 4. When you had y is equal to 4, you would just draw that horizontal line across 4. But we can talk about any function. There are going to be some functions that have periods where they behave like constants, but they're not constant. All right, a local maxima. When the graph of a function is increasing to the left of x is equal to c and decreasing to the right of x is equal to c, then at c the value of f is the largest. This is called a local maximum of f. So what are we saying? All we're saying is I'm going to put this in layman's terms here. I'm not going to talk about the mathematical definition. The math definition is having us think, okay, if we're increasing and then after a point we start decreasing, we've got a maximum. A much easier way to think about this is if you have the peak of a mountain. Whenever you're at your mountain peak or whenever you're at the peak of a hill, whenever you peak, you're talking about the maximum. It's not really hard for students to see maximums. This is something that you guys are usually really good with seeing right off of eyesight, especially when those points are labeled. So I'm not too worried about you guys being able to identify a maximum. A minimum is when you go from decreasing on the left to increasing on the right. So if we have a function that's decreasing, it gets to a point and then it starts increasing, we call that a minimum. Now both maximum and minimums are called inflection points. That's another way that we can think about them. An inflection point means that it's where it changes direction. And when we're talking about direction, we're talking about whether it's increasing or decreasing. And again, it's important to know your inflection points because when you get to calculus, you're going to need to know about if your first derivative is equal to 0, then you know that you're looking at, or if your first derivative at a value is equal to 0, well, then you know you're looking at an inflection point, so you know that on one side of it, it's increasing, and on the other side, it's decreasing. If it's a minimum, on the left, it's increasing, on the right, it's decreasing. If it's maximum, on the right, or on the left, it's increasing, on the right, it's decreasing. So again, knowing your minimum and maximums are going to become very, very important when you get to calculus. And I realize that I'm saying a lot here that doesn't make sense because you have no clue what a derivative is, but that's okay. I'm just emphasizing why you need to know these things. And then again, we've got a formal definition of a local maximum and minimum. I'm not going to go into all of this. You can read these yourselves. This is just the mathy way the textbook has it. But again, I think the easiest way to think about it is a maximum is the peak of the mountain, and the minimum is like the valley or the lowest point in the valley. All right, now I've got an example here, and the example is going to use the same graph the entire way through. Now, at what numbers, if any, does f of x have a local maximum? There's only one local maximum here. It's this point 1, 2. And it's because I'm going up and then I'm going back down. I've got like a peak to a mountain. It's going to be really tempting to put like a point up here or a point up here as a maximum. We're not talking about an absolute maximum. We're not talking about the highest value that the function has. We are just talking about a spot where the function was once going up and then suddenly changes to going down. And that spot for us is at the x value 1. So we've got a local maxima at x is equal to 1. And what is the local maxima? Well, that's where we give the ordered pair 1, 2. If you're asking where is the maxima, you're asking, okay, at what x value does the maxima occur? If you're asking for what the value of the maxima is, then I need to know both the x and the y because I want to know everything about the maxima. Now the next one is asking for local minimums. Well, local minimums, we've got 2. Local minimum is where you go from decreasing to increasing, decreasing to increasing. I've got 2 local minimums here. Again, we can see that at these 2 points, it turns around, it starts going back up. So that means this and this are my local minima. Now, where are they? We've got one local minima at x is equal to -1. We've got another local minima at x is equal to +3. And what are the local minima? This is where I put in my ordered pairs, -1, 1, and 3, 0. So those are my 2 ordered pairs. Those are my 2 local minima. It's all good. Again, I'm not too worried about you guys being able to spot those. That's pretty easy. Now, this is where it gets a little bit more complicated. List the intervals over which f is increasing. So when I'm talking about the intervals in which f is increasing, I'm talking about where it's going up. It's going up from -1 until 1 only in terms of x values. It also is going up from 3 until this graph goes on forever and ever and ever. When I talk about the intervals, it's asking for the intervals where it's increasing. I report them as x, so I can make these like vertical lines that go up where the function is increasing. And this is going to be defining where it's increasing. I only talk about these things in terms of x. I'm not going to use their y values whatsoever. I'm only going to look from x to x. The first x value where it's increasing starts at -1, and I put -1 in parentheses. I don't use a bracket for -1 because it's not increasing at -1. -1 is the minimum. That's where it's turning. Where you turn is not included as an increasing value. That is the point where it goes between decreasing and increasing, so I use a parenthesis. I say at the very first value after -1, this graph starts going up. It continues increasing until it gets to +1. At +1, we see another inflection point and we see it turn downwards. So I write 1. I am talking about an x1 to an x2. I'm not talking about the point -1, 1. I am talking about the point I'm talking about the x value of -1 to the x value of +1. I have to put a union because it breaks for a bit and it doesn't increase. And then it starts suddenly increasing again at that x value of 3. That's an x1. The arrows of this graph indicate that it will never stop increasing at this point. It goes up and up and up. We've seen all the fun stuff of this graph. And from this point forward, it's just going to behave according to whatever pattern it behaves, and it's just going to keep going vertically up and up. So that means it increases until infinity. And I'm referring to infinity as another x value. It's kind of tough to see that because you're probably thinking about infinity as a y value because it's pointing up. But remember, as it goes up, it still moves that way, to the right, towards infinity, for numbers going on forever and ever and ever. All right, so that's how I report my intervals when it's increasing, and I leave it like that. We always report in terms of x. We never think about the y values. Do not tell me that it's increasing from the point -1, 1 to the point 1, 2. Do not tell me it's increasing from the point 3, 0 to forever. You're using an interval notation to write this. We don't talk about the y values ever, 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 ever when we're reporting increasing, decreasing. Decreasing is going to be fairly similar. Now, difference here is that it starts decreasing at -infinity, and I've got this indication that if I were looking at this graph to the left, it's always decreasing. It's all, as I move from the left to the right, it's coming down and down and down until it gets to that point -1, which means that it started decreasing at -infinity. This is an x1 value. It stops decreasing when it gets to that point -1. And again, I put that -1 in a parenthesis because I'm talking about an inflection point. -1 is not decreasing. It's where it goes from decreasing to increasing. I then have a union symbol because it stops decreasing for a bit. And this actually, one of the things that helps out is I can look and I can see that the point where I say that it stops decreasing is a point where I say that it starts increasing. That's good. You should, unless you have an endpoint on your graph, wherever you have a point where it stops decreasing, it should immediately start increasing right after that point. It starts decreasing again at the point 1, which again holds up for me because I've got this point 1 where it starts to decrease again, and that's where it stopped increasing. And it decreases from 1 until 3. And again, I need that to work out because I've got this point 3 where it stops decreasing, but it starts increasing again. So you should have some level of that matching when you make these happen. If you are saying that it's like decreasing from -infinity to 1, and then it's increasing from like 2 to 7, but it's decreasing from 1 to 3, you're running into issues because you can't have all those overlaps. Now I can say that I've got the totality of this graph from -infinity to infinity covered. I know that the inflection points are at x is equal to -1 and 3. I know that -1 is my minimum, 3 is my minimum, 1 is my maximum, and that it's decreasing from -infinity to -1 and from 1 to 3, and it's increasing from -1 to 1 and 3 to infinity. All right, you have a homework assignment. I realize that this is a lot of problems, but we really need to get good at looking at graphs, knowing when they're increasing and decreasing, knowing our local minimums and maximums. If you have any questions or concerns, please reach out to me sooner rather than later. Again, especially if we're struggling with the interval notation, if we're struggling with how to figure out where it's increasing, decreasing, etc. But then keep working on the homework, reach out if you have questions, and have a great night.